All right, folks. So we've got this problem right here, which is about RC circuits, but it's a little bit more than that. It's really mostly about fully understanding Kirchhoff's loop law. And there actually are multiple solutions, but I want to think about this problem mostly from that perspective of the loop law. It's really intimidating at first when you see a circuit with so many elements sticking out of it, but we're going to try and piece it apart and see that each little part is actually not that bad, okay? So let's get to reading here. Consider the circuit drawn on the right. At time t equals 0 seconds, the capacitor has no charge on it. Find the current across R1, R2, and R3 at the following times. T goes to 0 seconds or t goes to infinity seconds. And so those two, the 0 and infinity, are really more indicative of the behavior here at this capacitor. That's what's going to be affected by the time. I'll point out also that this, where I say the capacitor has no charge on it at t equals 0, these are like keywords where I'm trying to tell you that this is a charging circuit as opposed to a discharging circuit. It's initially not charged at all, and then it charges up over time. And so the rules are just a little bit different, or the ordering in what happens is different for those two types of circuits. Let's look at this picture and let's really try and understand what it is we're looking at, specifically by drawing some loops, right? So Loop's law is all about going up some elevators and down some stairs here. If we go up this 4-volt elevator, right? The loop law says that by the time we get back to the bottom of the battery, we should go down by 4 volts. If we take this pathway here through R3, well, notice actually we're already back at the battery. We didn't have to go anywhere else, and we're already here at this 4-volt battery. If we went up 4 volts worth of elevators, in order to get back down to the ground floor, we have to go down 4 volts. And immediately, we actually already have that. There's nothing which is going to change, that we have to feel 4 volts at this third resistor. We are looking eventually to get to currents across those 3 resistor elements. And I want to remind you, each resistor is going to have its own version of Ohm's law, delta V equals IR. To get to the currents, we just have to realize that each element has its own V, I, and R, and so, delta V3 equals I3 times R3. We would then want to rearrange Ohm's law to solve for the problem. Let's look at some other pathways here. Let's take a little blue path where we go from the battery and instead go through the middle. Right, we get this choice. Let's go through the middle and go across this resistor, and then, well, we have to go through this capacitor. There's no other choices. You don't want to go backwards. You don't want to go up. We're trying to make our way back to the battery, and this is the way that you go. You would have to cross not just the resistor, but also the capacitor. This is where the problem gets dynamic over time because the voltage across the capacitor is time dependent. And let's take one more pathway where we go and go upwards across this resistor. And let's try and make our way back to the battery. We don't want to go left. We want to try and make a sort of direct path without going backwards. And we see that we also have to go across that same capacitor in order to make a loop back down to the bottom of the battery. And so this is what's going on here. It's actually just a parallel circuit, even though these 3 resistors aren't geometrically parallel. This one's perpendicular, but from the topographic perspective, it's parallel. You get a choice. You could take the purple path, the blue path, or the red path. If you take blue or red, you have to wrestle with what's going on at the capacitor. And what's going on at these two limits, going these extremes, 0 seconds and infinity seconds, those are actually very well described in terms of a capacitor. So since this is a charging circuit, if you look back at your notes here, we talked about what happens for a charging circuit. Remember that a capacitor is kind of like a bucket, and if it's originally discharged, it originally has no net charge on it. What's going to happen when we plug it in and turn on the circuit, an electron is going to come by and come to this part of the capacitor, the bottom part. And an electron that comes here is going to repel an electron on the other side, and it's going to go forwards. But that's just a regular circuit. If an electron comes out here, an electron goes through the capacitor up to the other side, that's how a regular circuit works, and that's what a current is. And so initially, this capacitor, it's no different from just having a wire installed in place of the capacitor. That's going to change as we build up charge on the capacitor. But for right now, at t equals 0, it behaves like a wire. Okay? For a time of infinity, the electron comes here, and we've already started filling up the capacitor. Over time, the more electrons that start ending up on this part of the capacitor that there are, the harder it is to fill it up. And eventually, it's all the way at max capacity. It's full. This bucket is full. I cannot fill it with any more electrons, and so I cannot move into that part of the circuit. You could think of this like a broken or open circuit where the wires just aren't connected, but I think it's better to think of it as a battery that's been connected in reverse. And so if current was trying to flow in one direction, this other battery, the second battery, is sort of counteracting that in the opposite direction. This point of view is a little bit more useful when it comes to thinking of discharging circuits, just to get this idea that the capacitor is like a charged battery in the opposite direction, at least briefly. Let's get back to the problem and get to solving. We actually already got to this beginning part, R3. Okay, we can actually do that one again, and we didn't have to understand anything new, right? We got that this is a 4 volt across. Delta V3 is equal to I3 R3. And then we can just transform this into the more useful version of Ohm's law by dividing both sides by the resistance. I3 is going to be equal to delta V3 over R3. And ohms and volts are already in SI. So this is say 4 volts and 500 ohms. So we don't have to worry about any sort of conversion. A volt per ohm is going to be an amp. So 4 divided by 500 is 0 0.008. 0 0.008 amps, or 8 milliamps. Okay, and actually, this is time independent. Whether time equals 0 seconds or time is infinity, an infinite amount of time has passed, doesn't matter because it's got to follow loop law. We went up 4 volts, we have to go down 4 volts. That's not going to change regardless of what the capacitor is doing. Let's follow one of these paths that do cross the capacitor. Let's go across this R2 path. Okay, and then we're going to go past the capacitor in order to get back down to the battery. Now this is going to be time dependent. Let's think about the time equals 0 case. So at time equals 0, the capacitor is going to behave like a wire, and the voltage across a wire, delta V, I'll say delta VC for 0, is going to be 0 volts. No drop across a wire, because anything that's metallic is an equipotential. It has the same, let's say, raw V value, so delta V is 0. And in real life, there's a very small, few millivolts worth of drop across a capacitor, across a wire, but in this theoretical case, there is no voltage drop across the capacitor if it's behaving like a wire. So let's go back to Loop's law. This is 4 volts up the battery, 4 volt elevator, and we have no drop across the capacitor. That means all of it is resting down the resistor. And so R2 is 360, V2 is 4 volts. and I2 is going to be 4 volts over 360 ohms. Okay, and once again, we don't have to contend with any sort of mismatched units. We just divide these directly, and we get that this is 0.011 repeating amps, 11 milliamps. Great. Let's do one more, and I'll have you do the last one yourself. Let's now talk about what's the same loop, but I want to talk about with the time infinity case. So same exact loop across that R2 resistor, but now t is going to be infinity seconds. Now, what is the voltage in this case? Well, at an infinite amount of time, the capacitor is full, and so it takes over the entire 4 volt voltage drop, and none is left for the resistor. And doesn't that make sense that a full bucket is not going to allow the charge to get through, and so therefore there won't be any voltage across the resistor, and therefore no current as well. I'll let you try and apply the same logic to the path with R1, but should be fairly similar. Okay. So hopefully that clears up any confusion. Hopefully, if you thought that this was an intimidating looking circuit diagram, that it turns out it's just a few things in parallel. Parallel in general tends to make things easier, but yeah, this is a pretty good problem to showcase mostly understanding loop law, Kirchhoff's loop law. All right, see you in the next one.